Hello, I'm Steve Johnson. Welcome to Digital Works TV. Our special guest today is John Vickers, and I'm actually not sure which of your titles or which of your positions to start with, so I'm going to kind of go from what feels like the top one down to the, well, they all feel important to me. So you're the head of the National Center for Advanced Manufacturing, correct?
That's right.
Okay, you are the NASA Principal Technologist for Advanced Manufacturing.
That's correct.
Okay, and you are the leader for Marshall Space Flight Center or the senior leader for advanced manufacturing.
That's right. Most of my time is probably as principal technologist.
Okay. And advanced manufacturing, that's
right.
involved in all of
That's
it.
right.
Because me not being an engineer, I've got to ask you, and I kind of think I get it, and maybe everybody watching this gets it but me, but what is advanced manufacturing?
Well, sometimes I'll say it's the big M, and what I mean by that is think about General Motors as a manufacturing company, Boeing making airplanes, that's a manufacturing company operation. So it includes the processes like welding or materials and those kinds of things. But I'm more focused on the big M, the big advanced manufacturing operation, all of it together.
Okay, so does that include, when I don't know why, but when I hear the word advanced, I think, well, he's talking about additive manufacturing, 3D printing. Is that
does include that? I should have said that.
Okay.
That's one of the most prominent and promising emerging fields. Not that old, it's only, since it was invented, might have been 20 or 30 years.
Yeah.
But we've only been using it for NASA critical operations like liquid rocket engines for 10 or 15 years. So it's not that, that's a really short amount of time for an advanced technology. So when I say advanced, I work at NASA, so almost everything's advanced.
I get that. I get that. Well, I remember when in my former career as a TV news guy doing.
We're not down at the muffler shop.
Okay, no. Yeah, which they would say is advanced manufacturing, and it can be.
Absolutely,
They're looking. Yeah. But I remember doing stories about figuring out if 3D printing could be used for rocket engines for SLS.
Absolutely.
And that is in fact happening, isn't it?
It is.
Some of them are being additive manufacturing is being used.
So I've got a really good story about that. Maybe 20 years ago, we were just getting started in additive manufacturing, and we had aspirations for things like rocket engines for future vehicles. We didn't have SLS at the time. Very senior propulsion engineer, smarter than me at the time, said, I don't think we'll ever be able to use that. Well, today, there's not a single rocket engine flying, not a single rocket engine in development that's not using 3D printing additive manufacturing. Some of them are almost completely 3D printed.
Wow, that's the
right.
story I did was probably 10 years ago, and I think it's come a long way since then.
It's moving fast.
Okay, so does advanced manufacturing that you do include us figuring out how to 3D print? I'm sorry, I call it that because that's the first way I heard it.
That's okay.
3D print using materials we might find on the moon or Mars. Is that part of what you think about?
Absolutely. So we have projects today at NASA Marshall for 3D printed structures. So habitats, etc., on the lunar surface or on Mars. And so we're using the material that we find there, we call that regolith sometimes, and we've been very successful at it, to build structures. There's a company that we've worked with that's taken that technology, and they're building homes. They've built a whole subdivision out in Austin, Texas.
I've seen. Yeah. It's pretty cool looking. I've seen
it
the
was a
pictures.
60-minute story.
Okay, so just out of curiosity, when you think of NASA, maybe when you think of advanced manufacturing, you think, well, that is so cool, and I bet it really does cost a lot of money. Is there a cost savings in using advanced processes, or like with 3D printing, I'll bet it was a lot more expensive at the beginning to do something than it is now, or am I just totally off base?
So we're always trying to reduce. We're trying to do three things generally in advance when we're trying to make advancements, and that's to reduce the cost. Everything we do in aerospace, NASA, Air Force, commercial aviation costs too much and takes too long. So we're constantly we're constantly trying to reduce the cost, reduce the time that it takes, but at the same time, we're trying to improve the capability.
Yeah.
That's that old faster, better, cheaper kind of
And
thing.
I've often heard you can do 2, but you can't do 3.
Well, I think today we're doing 3 in a lot of cases,
Okay.
and things like digital twins, which started as a part of advanced manufacturing, are really elevating our ability to be able to do that.
Okay, I'm going to ask you about the digital
I know
twin
you are,
thing in a
yeah.
second, but is that generally the case with advancements in manufacturing, that at first they're very expensive, but then it generally, if you use them long enough, it gets cheaper? Is that a way to look at it?
So, absolutely. Think about, I've used this as an example many times. Think about flat screen TVs. Remember when they came out?
Oh, yeah.
How expensive they were, right? I mean, nobody.
CD players the same way.
Same thing.
Yeah.
Now look at them. They're almost disposable.
Yeah.
I mean, they really don't cost, they're, a few $100 for tremendous television, So it's the same. So advancement, whether, the price of cars is not going down, but the capability, the complexity, for automobiles today versus when me and you first started to drive is tremendous. So
What are you trying to say? Just kidding. For me, anyway.
I don't know, feeling my age, I guess.
Okay. All right. So you said the words digital twin, and I have had this explained to me by the way, what kind of engineer are you?
So I've spent 40 years, part of it at NASA,
Yeah.
not all of it, in the materials and processes manufacturing engineering. So that's what kind of engineer I am. A long time ago, I went to college. I did both mechanical and systems engineering.
And we're, by the way, going to get around to model-based systems engineering. We always get around to it here. But you mentioned the words digital twin, and like I said, I've had it explained to me, but I'm not sure it completely took. So could you explain that, and so we could talk about that a little bit?
Yeah, people ask me that all the time, and I have tried to come up with a 1-sentence, 2-sentence
Oh, you can do a paragraph.
explanation for that, and it is tough. Let me start by saying, so the National Academies just last year put out a report, and they did a pretty good job at a definition for digital twins. This report was on digital twins research and development that we should be doing in the future. That's what it was about. And they said, if I can recall it correctly, they said that a digital twin is a virtual construct, that means a computer model, that mimics the context, the substance, the behavior of an engineered, a natural, or a social system. And so they really expanded the definition when they did that. But most of our work prior to that had been around engineered systems, not the natural and not the social. So that really, made people think and expanded what it was. I think that there's a few elements to a digital twin that helps to explain it. It needs to be something, it's a computer model. So when somebody says, oh, it's just a computer model, well, it is a computer model, absolutely. But it is a special, extraordinary, more than what you thought about previously as a computer model. So it tries to represent, a whole real thing, system, for example, automobile. It has predictive capability, so it can see, it takes where we are today, and that's the one thing about digital twins. Where we are today is not really the thing about a digital twin. It's where we're going to be in 10 years, in 20 years, in 30 years. So it has built into it a predictive capability. So those are a couple of the elements.
Okay, so
it's a whole picture, and it can predict into the future.
Okay, before we get to, I just started thinking this when you start talking about it. In video games, when there's an avatar for the game player, is that a digital twin?
So not really. I'm not the digital twin police, so I don't get to say what is and what's not. And I'll give you an example that's sort of like that, but it doesn't have physics in it. And so the real thing for engineers is that we when we're describing the behavior of something, airplane, automobile, etc., we need to have it's got to obey the laws of physics.
Okay.
You know those
All right.
video games don't.
Yeah,
obey.
you're right. So jumping 200 foot.
That's right. But let me say,
crevasse is not the same thing.
let me say, so recently Microsoft did a virtual scan with photographs and LiDAR, for example, of the Vatican. And so inside and out, you can tour the Vatican now photorealistically, in what they call a digital twin of the Vatican. Now, some people would argue that's not really a digital twin. It doesn't have all that physics that I described earlier. It's got dimensionality, but
if it had a moving part,
would
that make it a true digital twin?
So I said some people. I'm not the police.
Okay.
If Microsoft
Yeah.
and the Pope says it's a digital twin, it's a digital twin to me. So
Okay, so in model-based systems engineering,
yeah,
it's digital. It's on the computer. So if you had I'm getting in the weeds of not being an engineer here, but how does the digital representation of a system that a systems engineer is working on, and he has modelers and if something has changed, you can see how it changes everything. How is that digital representation? And this is where you get to tell me, Steve, you didn't say that right. But is that a digital twin?
absolutely can be, and it's it's a really good example. And much of what we do in digital twins today was born out of systems engineering.
You want to have a drink?
I do. Can I get a drink?
Okay. Yeah. Just move your. Yeah. Just push it forward. Yes, this is not. Well, it is recorded, but it's not edited. Okay. Pull your mic back. All right. So go ahead.
So I was saying much of where digital twins are today was born out of systems engineering, because we were trying to cover with a computational process the entire life cycle. And so that's what systems engineering does.
Yeah.
It treats the whole life cycle. What systems engineering sometimes doesn't do is get deep into the behavior of a physical system.
Okay.
And so it sort of lacks that part of it sometimes. But it's a great example of a digital twin. When it covers that whole capability, that's a big element of a digital twin.
Okay. So it sounds like digital twin is going to become that's going to be a phrase or two words that more and more people will know about and understand, just like, well, I won't say like AI, because I'm not sure anybody or a lot of folks understand what AI is. But am I right about that this is the coming thing?
Absolutely. So it is growing. AI is maybe the biggest digital transformation tool or application because of you see it on the news, the notoriety of it. It's extremely capable. Yeah. Everybody's using it almost in their daily life. So digital twin's not quite where AI is in its, recognition of the public, but it's absolutely being recognized by certain communities, engineering communities, automotive. Airbus, just within the last month or so, made a advertisement, that every airplane that they build from now on, they'll build a digital twin of that airplane before they build the physical airplane.
Okay, so we started out talking about advanced manufacturing and how that is making things cheaper and allows you to be faster and better. Is the digital twin going to do the same thing? When you look at it, seeing as you think about it you're not the police, but you think about it, does it look like, man, this is going to make things in the future so much easier?
Yeah. So when we first conceived the digital twin, of course it was built on some work we had done previously, but one of the primary goals was to be able to do work in a virtual environment as opposed to doing experiments in a physical environment. We could do many more. We could do them much faster. We can even conceive of we can do them better, because a physical experiment is limited too. So certainly we were one of the primary goals was to reduce the cost. Everything we do
Yeah.
in aerospace today costs too much and takes too long. And so,
Yeah, that's probably it. Everybody would agree with that. Use the word predictive. How is a digital twin predictive? What does that even? I mean, when you say predictive, it's like it's going to tell you, "Hey, I'll work better if you do this." But that what do you mean when you say that?
well, that is sort of it. So I always go back to, I'm thinking about engineered systems,
Yeah.
for example. So if let's just take a car. Everybody sort of recognizes that, and so the computer in a car today sort of acts like a digital twin. There's hundreds of sensors in a car today, all feeding information to a central computer so that car can operate optimally, I guess, and can operate, and gets the best gas mileage.
Yeah.
So the predictive capability could tell you how that car is going to operate. It could tell you, your tires are going to wear out. Your oil needs changing in the future. So that's a sort of a simple example, but that's what we want to be able to do with digital twins. Look into so we're trying to describe behavior, how something's behaving today. We want to know how it's going to behave in the future. Another great example, there's a couple of really large organizations that are working on digital twins of the global environment. So the weather, the ecosystem, we want to be able to predict, it's in the news every day, how that's going to look in the future. So that's what a digital twin.
Okay.
So a digital twin of the Earth, we want to predict how it's going to look in the future.
Okay, so it sounds so much like what I'm already thinking of as AI, the ability to predict if it has all the information. I'm assuming digital twin, since that is a creation. Am I correct?
So think about the digital twin as this central hub. AI as a tool, virtual reality as a tool. So these sensors, Internet of Things devices, those are tools. They happen to be physical tools. Model-based systems engineering. All those operate sort of on their own and in a little bit of a silo. The digital twin assimilates all that information together, and that's what's why when I said it's an extraordinary computer model.
Yeah.
So we're taking all that data, all that information, so that we can predict, make informed. We're really just trying to make decisions based on that information.
Okay, so back to MBSE. If you're a systems engineer, you have to be salivating over this a little bit.
Absolutely,
That something is going to not only help you do your job now,
Yeah.
but it may predict things that you ought to think about changing for the future. Is that a
Yeah, that's a key element in the digital.
Yeah.
So when I spell out those 3 or 4 things that make a digital twin, I always say the predictive capability. So being able to look into the future, but still, we're digital twins, just like a lot of these other digital transformation approaches, are very nascent. We're just those are emerging. We can't even. I heard a Bill Gates interview recently. He said, we don't know the upper bound for these things. The potential is immense for these things.
well? So, and I need you to be predictive. When will we get to the point? I mean, I'm sure you're involved with it, so you have your. Man, I'll be so glad when we get here. But say, where will we be 10 years? Can we even conceive?
It's hard to.
Of where we'll be in 10 years on this stuff?
So I'll give you an example, and you can all go off and look on the internet. In 1994, there was a Today Show episode where Bryant Gumbel and Katie Couric sort of just discovered the internet.
Yeah.
It just Bryant Gumbel says, hey, what is this internet anyway? 1994. So that was 30 years after. That was 25 years after the internet was invented.
Yeah.
Now we're 30 years after that. So look at that progression between 1994, where we almost didn't know what the internet was, and the digital cell phones and internet and AI.
I mean, it's basically our lives.
Oh man,
Yeah.
it's just
Yeah.
so that's why they call it a digital transformation. It is transforming the way we work and live. And so 10 years from now, so I believe, so I was able to watch those 50 years of progression to today. And so what I see is that it's accelerating so much faster. Just think about, 5 years ago, did you even hear of AI much, right? Think about where we are today.
We did in the movies.
But it's every
Nobody about
day.
it
That's
real.
right. iRobot or something. You saw it in the movies.
Yeah.
And by the way, I do watch these sci-fi movies to get a feeling of how we can. So what we want to do is we want to make it happen faster.
Okay.
That's the key. That's the key to folks in jobs like mine. It'll happen naturally in 10 or 20 or 30 years. I don't want it to happen naturally. I want to feed it. I want to accelerate it. I want that 10 years to be 5 years.
Okay,
That's what
so
I
you're
want.
wanting digital twin to become where we know it as well as we know AI.
Oh, yeah.
Okay, so got to ask you, anything scare you about any of this stuff? I mean, so you're somebody who deals with it every day. Do you know? Because like the average person's going, man, I don't know. I think we even had we chatted about that. But is there anything about this that you think, Steve, we need to keep a watch on this?
So when 3D printing first came out, there was a concern that you could 3D print guns and take plastic guns and take them into the Air Force. And so some of us were called to Washington. Some of us got a visit from some of those agencies that just have 3-letter initials, and they said, we want to put a stop to this. And so the technologists say, you can't stop it. You're going to have to take another approach. And so I've consulted with some of those agencies about how do they address cybersecurity is a really big problem for them today. And so they want to slow it. Well, there's no slowing it. So we're not there's just not. You just can't stop technology. AI is here, and so we're going to have to manage it. Things can go wrong and will go wrong, but we're going to have to. We have a term that we call a phrase that we use. It's verification, validation, uncertainty, quantification, VVUQ, and so we use that approach to make sure that the software. I did hear the other day that they ran some tests and they tried to tell this AI system to turn itself off, and it refused to turn itself off. And I was like,
that is not making me happy.
I was like, that is not. But we're going to have so we're very adept at managing how software behaves, and it is just software. And so, but we got to manage how.
Well, so and I've heard more than one AI expert say, no, let's don't call it that. Let's call it machine learning. Which, if I think about it that way, that the computer learns from the input, it doesn't seem as
so. There's
scary.
there's an academic distinction in AI and machine learning.
Okay.
Yeah. So they're very similar, but there is the academics distinguish one from another.
Okay, so
don't ask me to do that today.
Okay, all right. So from this conversation, in the future, when we think advanced manufacturing, we're going to be thinking digital twin.
We are, and we're going to be thinking it's a convergence of a lot of technologies. Yeah. Robotics is one of those things that it's going to be highly. We use a phrase, model-based everything, and that's what I think. Everything's going to be driven by computational model-based approaches.
Okay, and wow. Well, thank you.
You're welcome.
Thank you. I actually feel a little smarter. That's always a good thing for me. Thanks for being with us, John Vickers.
You bet.
And thank you for being with us, and keep watching Digital Works TV, and remember, it works.